this video will work through the problems at the end of the frequency distribution lecture slides. I hope that you have tried to work through these problems on your own before watching this video. That is the absolute best way to practice. The only way to know what you don't know is to test yourself. And there's no harm in doing a problem incorrectly at this stage in the game. You're going to be able to be walked through the answers, but it's more effective if you get the answers after you've already tried the problem. Okay, so the first set of questions ask you to identify shapes of different distributions. And these are the distributions that you already saw in the lecture. Now, before I start to talk about the shape of this particular distribution that's looking at different majors among students, so along the x-axis are the different majors, along the y-axis are the frequencies, the number of students that are in each major, I have to point out, major is a nominal variable. And as I've mentioned before, the shape of this distribution is pretty much meaningless because there is no strict guidelines for the order in which the variables appear along the bottom because it's not numeric in nature. Now, whenever we're looking at a variable that is numeric in nature, you start from the low end on the bottom left and you work your way to the high end all the way to the right. So from low to high, left to right on the x-axis. Major, there's no quantification of major. You can't say, oh, well, biology is less than psychology. I mean, you could because you have a bias, but it's not inherently numeric in nature. So I just wanted to point that out, that although I'm asking you to identify the shape of this distribution, for nominal variables, the shape is pretty much meaningless. But just as practice, what is the shape of this distribution? Well, we can see that it's unimodal, and that's actually useful information. The mode is something that you'll find out soon enough that you use to describe nominal variables. We could say, yeah, the pre-nursing majors are the most common majors among students in this class. So here's our peak. There's our unimodal distribution, just one mode. You can also see that it's not symmetrical, but that's not that meaningful because if you place these variables in such a way, you could try to get it kind of symmetrical. Because remember, the order along the x-axis doesn't matter. But what I'm really getting at when I ask you about shape, I'm asking, are we looking at a normal distribution or are we looking at a skewed distribution? And if it's skewed, is it a positive or a negative skew? Well, the best way to try to look at the shape is to just draw a line if you're using bar graphs or histograms. It kind of represents the general trend in the data. So I'm looking at this, and remember in the video I said sometimes it's hard to identify positive versus negative skew. I'll tell you right now, it's one of those. It's definitely not normal, right? We don't have a situation that looks like this, so it's not normal. So it is skewed, but the question is it positively or negatively skewed? So the skewness gets at the tail end of the distribution, which is going out to the right. So if these variables were numeric order, you would say that most people fall in the low end, and then some people fall in the high end. Fewer people fall in the high end of the distribution. I also told you as kind of a hint, if you're thinking about a positively skewed distribution, the word positive starts with the P. So if you flip the graph over like this, and you've got a situation, so if we flip it over, you're going to have, your x-axis here, and let's see, and your frequency here. You're going to have something that looks like a P. P for positive, so positively skewed distribution. All right, let's move on to problem 1B. So this graph should be familiar to you. It's looking at the number of missed sticks for blood draws this week among a sample of phlebotomists, or no, population of phlebotomists is what we were looking at. And much like the first graph that we looked at, you have your variable represented along the bottom, the different values for missed sticks, and then your frequency represented along the vertical, the y-axis. Well, looking at this, the shape looks pretty similar to something that we just looked at. It is unimodal. You see that one peak here. There's only one value that's most frequent. And, lucky for the people going to Quest Diagnostics, that's 0 missed sticks, so that's a good thing. And also you can see that it is a positively skewed distribution. If you turned it over this way, it looks like a P, kind of. And the skew goes out to the high end. So another way to think about remembering positive versus negative skew, the skew refers to the outliers, the tail of the distribution. And positive, you can think of it as a larger number. So positive skew, tail out towards the larger number, whereas negative skew, if the tail was over here, you could think about it, the skew or the tail is towards the smaller number, which is more in line with, negative than the word positive. However you need to think about it to remember it is up to you. Then item C for problem 1 in the example problem. Looking at this doesn't look like the other two graphs if we're looking at the data. Again, you've got the different values for your variable along the x-axis and the frequencies corresponding to each along the y-axis. But this time, our outliers, our skew, is more out to the low end of the distribution, whereas most people fall in the high end of the distribution. And if we flip this towards this way, it does not look like a P, so I'm going to go ahead and call this a negative skew. Whereas the other ones were a positive skew. I'm going to just, oh, there we already got it there. Okay, negative skew. Also, this is unimodal. Right here, it looks like the bulk of patients were between ages 40 and 49. So if we were thinking about the example in the previous video and, is there some kind of relationship between age and this outbreak, I would start to think that patients in their 40s are probably the highest risk population, followed by patients in their 30s. Now, some people are really strict and they say in order to call a distribution multi or bimodal, you have to have multiple values in your data set that occur the most frequent and that occur the same amount of frequencies for the most frequent. So for instance, you could make the case that this is unimodal because 40 through 49 occurs 8 times more than anything else. But you could also make the case that there's 2 modes here, right? There's 30 through 39 also occurs more frequently than the vast majority of the other age groups. All right, example 2. Now we're finally ready to create a frequency distribution table and graph. So looking at this problem, it's asking you to create the appropriate frequency distribution table. So remember, I put the word appropriate in there because you do have to make a judgment call. If you have a large range of values in your data set, or in other words, a large amount of difference between your low end and your high end of your responses in your data set, then you probably need to do a grouped frequency distribution table. Because remember, the purpose of a frequency distribution table is to simplify your data. And if you have a situation where you have values in your data set that have a large range, you're going to have tons of rows in your frequency distribution table, and it's not going to be very good simplification of your data. On the other hand, if you have a small range of values in your data set, you can go ahead and use the traditional frequency distribution table where each value is individually on its own row. And that's the case here. The low end is 0, the high end is 5, so I'm going to go ahead and use a traditional frequency distribution table. Well, then you're also asked to create the appropriate frequency distribution graph for this data, and that requires knowledge of the scales of measurement. Now, I typically think of Likert scales like you see here, where you're rating something on a scale from 1 to 10 or 0 to 5. I usually think of those as interval scales. And that's because not only do you know the direction of the difference between values, but you know the magnitude of the difference between those values. I don't call it a ratio scale because there isn't a true 0 point here. You could say, yeah, there's a 0, means not at all satisfied, but you could make the case that that doesn't represent a complete void of satisfaction. So typically with Likert scales, I call those interval. If you have a situation where you have a Likert scale that represents the frequency of something, so like 0 would be never and 10 would be all the time, for instance, you could call that a ratio scale because 0 represents never, complete lack of whatever you're measuring. So looking at that, I know that I'm looking at an interval scale, so the graph that I'd want to use would be a histogram, or you could use a polygon. I like histograms. If you have a preference for polygons, that's fine as well. Both are appropriate for interval data. So I know I'm going to be creating a basic, traditional frequency distribution table with each value represented on its own row. And then I'm going to be creating a frequency distribution histogram with the data in that frequency distribution table. And this is just looking at customer satisfaction among a sample of 50 AT&T customers. So once you do that, you need to identify the shape of the distribution based on the pretty picture we're going to create in the frequency distribution graph. So let's go ahead and start by creating the full frequency distribution table. So remember, the first step that you want to do is create a table with all of your different column labels. So I'm going to go ahead and have customer satisfaction, and I'm going to just abbreviate that, customer satisfaction. Then I'm going to have the frequency of how many customers rated themselves with a particular level of satisfaction. Then I'm going to have the proportion or the probability associated with each level of customer satisfaction, then the percent, and then the percentile. I'm just going to draw a line under this and start plugging in my values. So I already mentioned that the range in our data set goes from 0 to 5. So the first step, well, the second step really, we've already created our table. We need to start putting in all the values in our data set from highest to lowest, top to bottom. So we have 5, 4, 3, 2, 1, and 0. Now it's worth mentioning that even, let's say I didn't have any 4s in this data set, I would still need to have a 4 represented in this first column because you want to represent the full range of scores from highest to lowest. All right, the frequency of each. So if I count, how many 5s are there in this data set? So I see 1, 2, 3, 4 5s. So that's the frequency. There's 4 5s in my data set. If you count the number of 4s, you'll find that there are 6 4s, there are 13 3s, there are 14 2s, there are 8 1s, and there are 5 zeros. Now, one way that you can check your work at this point is if you are given the sample size. So right here, I give you that sample size. That is your n, and it's lowercase n because we're talking about a sample. You can make sure that if you add up your frequencies together, you get that sample size, just to double check that you have captured all of the data points. So if we do the sum of frequencies, which is equivalent to the sample size, so 4 plus 6 plus 13 plus 14 plus 8 plus 5 does in fact give me 50. So I'm feeling pretty confident that I did count all of the values in the data set correctly. So the next step is to find the proportion of customers with each level of satisfaction, or the probability of randomly selecting a customer with a particular level of satisfaction, however you want to think about it. Regardless, P is what we're looking for. So remember, the formula for this is to take the frequency for the value of interest and divide it by the total sample or population size. So if 4 out of 50 customers have a level 5 satisfaction, I'm looking at a proportion of 0.08. If 6 out of 50, 6 is my frequency, 50 is my total sample size, 6 out of 50 have customer satisfaction rated as 4, then the proportion of customer satisfaction, people who rated themselves satisfied at a level 4, is 0.12. Moving on down, 13 out of 50 rated themselves with a 3 for customer satisfaction, representing a proportion of 0.26. 14 out of 50 rated themselves as a 2 for customer satisfaction, giving me a proportion of 0.28. 8 out of 50 rated themselves as a 1 for customer satisfaction, giving me a proportion of 0.16. And then 5 out of 50 rated themselves as not at all satisfied, or a 0, giving me a proportion of 0.10. So I've got my P's all filled out and ready to go. If I add these up and I get something that's close to 1, which you actually do get 1 perfectly, there's no rounding error in this case, that's a good sign that you did something correctly. Just like if you add up all your percentages and you get 100%, that's a sign that you didn't miss anything. So let's go ahead and fill in the percentages. you simply take P and multiply it by 100. So 0.08, I'm not going to show the calculations here. It's pretty straightforward. You essentially just scoot your decimal place 2 places over. Scoot your decimal over 2 places. So 0.08 times 100 will give you 8%. 0.12 times 100 is 12%. 0.26 times 100 is 26%. 0.28 times 100 is 28%. 0.16 times 100 is 16%. 0.10 times 100 is 10%. And then if I add all these together, 8 plus 12 plus 26 plus 28 plus 16 plus 10, lo and behold, I get my 100%, meaning that the entire data set is represented in this table, 100% of it. Okay, let's move on to the percentile column. So this one's a little bit more complicated because you do have to use the percentage for the next highest value and add it to the percentile for the lower value. But I'll show you how to do it. We'll walk right through it. Now remember, the percentile tells you the percentage of people in your sample or population that have a score at or below a particular score of interest. So that's why you start at the bottom and work your way up. So starting with 0, you literally just copy over the percentage of people with the lowest score, in this case with a 0. So 10% of this sample rated themselves as 0 or lower. Well, there's nothing lower, so we're just looking at how many people rated themselves as 0. So moving up, you add the percentile for the value that you just did to the percentage for the value that you're interested in. So 10 plus 16, somebody who rated themselves as a 1 in customer satisfaction is at the 26th percentile, meaning that 26% of the sample rated themselves as a 1 or below for customer satisfaction. Now moving up, I take my 26, my percentile for the value just below, the one I'm interested in, plus the percentage for the value that I'm actually interested in. In this case, I'm looking at 2, and we've got 28%. So 26 plus 28 gives me 54. And moving up yet again, so 54, the percentile for the value just below the one I'm interested in. Now I'm interested in a value of 3. The percentage of people with a value of 3 is 26, and 54 plus 26 gives you 80. So somebody who rated themselves as a 3 for customer satisfaction is at the 80th percentile, meaning that 80% of the sample rated themselves as a 3 or lower on satisfaction. Now I take my percentile for the value just below the one I'm interested in. Now I'm interested in 4, so the percentile from 3 plus the percentage for the value I'm interested in, so the percentage for 4. 80 plus 12 gives me 92, and then finish off with 92 plus, now I'm looking at a value in customer satisfaction of 5, and that is 8% of the sample had a value of 5, and I have 100. So this is a good sign. Remember, I told you that these two values should be the same if you did your percentiles correctly, and they are. And think about percentiles. This tells me that 100% of my sample had customer satisfaction of 5 or below. And that is pretty clearly the case. There's nothing above 5, so everybody had a 5 or below. So that just gets at the frequency distribution table for this data. Now let's look at creating the frequency distribution graph, which we already identified needed to be the histogram, and then identifying the shape of that distribution. So when you create your frequency distribution graph, you first want to plot your y-axis and your x-axis. Now remember, your x-axis represents the different values for your variable. So let's go ahead and provide the label for what we are measuring. We're measuring customer satisfaction. I'm going to abbreviate that. And then you want to represent the full range of values in your data set from lowest to highest, left to right. So we're going to have 0, 1, 2, 3, 4, and 5 here. The next step, we want to create the frequency along the y-axis. So the frequency You could also label this number of customers if you want to be more specific. So how many customers had a level of satisfaction at any given level. Now we are going to draw bars above each different value in our data set on the x-axis, and the height's going to correspond to the different frequencies in our data set. Now let's go ahead and look at our frequencies and be strategic about how we want to label this. I personally don't want to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 all the way up because we have to get at the highest frequency. So I'm going to go ahead and count by twos along my y-axis. And that's perfectly okay as long as it makes sense and it's simplifying your data. So this will be a 0. We have 2, 4, 6, 8, 10, 12, and 14. I think it's good for you guys to see me do this manually by hand so that you don't have to feel like your graphs have to be beautiful, because this is not going to be beautiful, but it's going to be good enough. If you want to make it beautiful, you do it in Microsoft Office or in Microsoft, some Excel or Word or whatever. Okay, so here we go. Value of 0 for customer satisfaction. So I'm looking here. So there are 5 customers with a satisfaction of 0. So 5's right about here. And when you draw this out, even though it doesn't have to be perfect, try to make it so that your bars touch halfway above and halfway below the value in question. Okay, so how many customers rated themselves as a 1? 8 rated themselves as a 1. So, and there we go. How many rated themselves as a 2? Well, you can see 14 did. So all the way up. And there we go. For 3, we had 13 threes. So right about here-ish and down. And then for 4, we had 6 4s. 6. Just kind of go over. And there we go. And then for 5, we had 4 5s. And there we go. So I'm looking at my histogram, and I'm trying to identify the shape of the distribution. And if I trace over the tops of these bars, I start to see my favorite shape in the whole world emerge, and that is a normal curve. Statisticians love normal curves, and you're going to find out why for the rest of the semester. But I'm looking at this, the normal curve. The bulk of customers are right in the middle, around a 2 or a 3. And then you have some who are extremely satisfied, and then some who are extremely dissatisfied. All right, let's move on to the next example. So example 3 is quite similar to example 2, where you're being asked to create an appropriate frequency distribution table and graph and identify the shape of the distribution. And if we're looking at this data, remember, we have to think about what's the appropriate frequency distribution table. Do I have a large range of values in my data set or a small one? I'm looking at this data and I see a high point of 219 is my largest value in my data set right here. And 32 is the low end. Well, if I were to create a traditional frequency distribution table with each value represented on its own row, I would have 188 rows. That is not simplifying anything. So let's not do that. Let's go ahead and do a grouped frequency distribution table. And then thinking ahead to the kind of graph that I'm going to create. If I'm looking at the number of credit hours, well, that is pretty clearly a ratio variable. You know the magnitude and the direction of the difference. So you know that somebody who took 5 credit hours took 5 more credit hours than somebody who took 0. Not just that they took more, but how many more. You also have a true 0 point. If somebody says, I've taken 0 credit hours, they have taken no credit hours. There's a complete lack of credit hours. So it's a ratio variable. So we are going to be graphing this as a histogram here in a little bit. Okay, so let's go ahead and go through all the steps of creating a grouped frequency distribution table. So remember, you want your classes or your groups or your intervals, however you want to call them, I usually call them groups, to be mutually exclusive. So meaning that there's no values that overlap across the groups. There's no double counting. Each frequency represents a unique person. Also, we want the groups to be all-inclusive. We want them to cover the full range of values. We want each group to have an equal width that's easy to count by, so we need to have multiples of 2, 5, or 10. And then we want to make sure that each group starts the multiple of the class width so that it's easier to detect the group width. Okay, so we also want to have a manageable number of groups that provides adequate detail. And kind of a rough criteria for that is you want to have about 5 to 20 classes at maximum. So the best way to begin thinking about creating an effective group frequency distribution table is to identify the number of groups using the 2k greater than or equal to n rule. So 2 to the kth power is going to be greater than or equal to, in this case, we'll call this a sample, lowercase n. So you need to start plugging in values for exponents to get to a value of 2 to some exponent that gives you a value that's greater than or equal to, in this case, 20, because that is the n in this example. So I'm just going to start with 2, because I'm not going to start with 1. 2 to the 1 power is just 2. So if I go, okay, 2 squared is equal to 4. Well, that is not greater than or equal to 20. 2 cubed is equal to 8. That's not greater than or equal to 20. 2 to the 4th power is 16. That's not greater than or equal to 20. 2 to the 5th power is equal to 32. And that is greater than or equal to 20. So I am going to say that k is equal to 5. This guy right here, our k. All right, so once we've identified what k is, the number of groups that we're going to strive for, we need to identify how large of a width we want each group to be. So the way that you find that is you take the largest value in your data set. So the largest value, remember, identified as 219. Subtract the smallest value in your data set, which in this case is 32. And we're going to divide that by k that we just found, which is 5. Well, 219 minus 32 is 187. Divide that by 5, and we get an ugly number of 37.4. Remember before I said that we need to have a width that's easy to count by, and I am not trying to count by 37.4. But we can round this up to a multiple of 10, which is easy to count by, and that would be 40. So that is going to be our group width. So we've identified that we have a width of 40, and we can begin to create our table. So we know that we have to cover the full range from 32 to 219 using a width of 40. So if I think about, okay, well, 32 is less than 40, so I need to start at 0. So I'm going to start from the bottom and work my way up. So we've got 0, counting by 40, the low end. Remember, the low end of each width or each group needs to be a multiple of the width of the categories or the groups. So 0, 40, 80, 120, 160, and then 160 plus 40 is 200. So these represent, I'm going to go ahead and delete this now, the basis of the number of credit hours, the grouping for that. So number of credit hours. So just like the traditional frequency distribution table, you want to label each column. So now let's go ahead and finish these groups. So let's go ahead and start at the bottom. We've got our low end. Now let's go from 0 to just below the low end of the next group, so 39. Then 40 to just below the low end for the next group, so just below 80 is 79. And then 80 to just below the low end for the next group, which would be 119, is just below 120. Then 120 to just below the low end for the next group, So 159 is just below 160, and then 160 to just below 200, so 199, and then 200 to what would be the next group would be 240, so we'll call it 239. It's just below 240. So we have mutually exclusive groups that are all inclusive. There's no overlap, and the full range of values is captured there. Now the next part, we need to identify how frequently occurring is each number of credit hours, or in other words, how many students have that number of credit hours. So between 200 and 239. So if I'm looking here, between 200 and 239, 1, 2, that's it. All right, so 2. Between 160 and 199, if you count that up, there's none of those. Between 120 and 159, there's 3. Between 80 and 119, there's 5. Between 40 and 79, there's 8. And between 0 and 39, there's 2. And just to double check, we can add all these numbers together. So we've got 8 plus 2 is 10, 15 plus 3, 18, 20. The sum of the frequencies is equal to 20, which is equal to the sample size that was given to you in the problem right here. So we know we didn't miss anything, or at least we're pretty confident that we didn't. All right, so now let's go ahead and create the histogram for this data. So draw my y-axis, my x-axis. Along the x-axis is going to be my number of credit hours. Let's go ahead and label that. And let's go ahead and put each group from lowest to highest, left to right. So between 0 and 39 credit hours, 40 to 79 credit hours, 80 to 119 credit hours, 120 to 159 credit hours, 160 to 199, and then 200 to 239. Should have made myself some more room there. My goodness. All right. So then along the y-axis, you have the frequency, or in other words, the number of students. So how many students had each of these credit hours? And I'm looking at my frequencies, and it just goes from 0 to 8. I'm just going to go ahead and count by ones then. So 1, 2, 3, 4, 5, 6, 7, 8. All right. So between 0 and 39, there was 2. Remember, we want our bars to be halfway above and halfway below each value and to touch, because this is a histogram for ratio data. Between 40 and 79, we had 8. So all the way up. Between 80 and 119 was 5. Between 120 and 159, there was 3 students. Between 160 and 199 was 0. And then between 200 and 239 was 2. So this illustrates one of the primary reasons why it's important to include the full range of values even if there's none there. Because when you go to draw your graph, it's important to see that, whoa, something just dropped off the map there, right? Like there's a gap in this spot between 160 and 199 credit hours. You want that represented in your graphs. So if I were to look at the shape of this graph, I could quickly identify that it is unimodal. There's one clear, most frequently occurring score, and that would be, right here. It's my peak. And then if I draw a shape, just kind of tracey, I can look at this and say, this is a positively skewed distribution. The tail is to the right on the high end, and if I flipped it like this, you would see kind of a P shape there. So it's a positively skewed distribution. So hopefully you did these problems in advance and you got everything correct. And even if not, that's a learning opportunity. If you didn't get it correct, now you see the correct way to do it and you won't make the same mistake twice.